Welcome to the satellite communication course. Today we will learn that what is the satellite location from an earth station or position of a satellite from the earth station. So to obtain the position of a satellite, so then we should know that what will be the here actually here is the solar panel. So to obtain the position of a satellite, we need to consider this two term, that is a azimuth and a elevation. That these are the 2 point or these are the two angle that to be obtained, or you can say that look angles of a satellite from an earth station. This is about a earth station, and these are these two angles, or you can say that these two angles are nothing but the look angles of a satellite from an earth station. So now to obtain the azimuth, we should know that from this geographical condition of the satellite, and we need to draw the diagram in such a way that we'll get that a horizontal surface of a satellite there. Now here this one is about a earth station, and we consider that this from this earth station to the satellite location, we consider that is about a position, and this one is a local horizontal. Here we can say that this one is the local horizontal, and from this local horizontal, okay, toward the satellite, okay, from this particular line drawing from the earth station to the satellite here, so that is nothing but the elevation. Okay, that angle is called as a elevation angle. This is nothing but what? A local horizontal. This one is nothing but a local horizontal, and this angle is called as a elevation. Now here, a ground station, and from that, or you can say that projection, this particular line of satellite, projection of the satellite path on local horizontal. Okay. Now from this, okay, from this, if you see that this is about a position, so we have the Earth station here, so we can say that this direction is, we can say that is about a geographic north. Or geographic north means what? We have a satellite in a orbit, but this geographic north is from the Earth station, and this becomes that whatever the angle we say that from this geographic north to this particular here horizontal here position, that is called as a azimuth. Now, what do you mean by this particular azimuth angle and the elevation? That elevation is the angle, generally it is measured from the trajectory of the satellite on the local horizontal plane. Okay, trajectory. This one is nothing but what you can say trajectory of a satellite on a local horizontal plane. So for that purpose, we should know that what will be the subsatellite point and trajectory, or that is nothing but a path from what a local horizontal plane to the satellite in the upward direction. Okay, that is about we can say that a angle measured from the trajectory of the satellite on the local horizontal plane. This is about a local horizontal plane here to the satellite in a upward direction. Okay, to the upward direction. That is nothing but a elevation. Or in another way, we say that the elevation of a satellite is the angle which a satellite makes with the tangent at a specified point on the earth. Okay, that is nothing but a what we can say that a elevation is nothing but what? The angle that is made on the tangent. Okay. So now for that purpose we need to redraw the satellite here, that satellite and that earth station here. So we consider that this is nothing but the earth now. Okay, this one is nothing but the earth surface here. We have the earth here. And from this earth, we say that here is a satellite. That is about a position of a satellite. This one is nothing but the position of the satellite. Now from that, if you draw a line, and this is about your Earth curvature here. So this is nothing but what? A point. We can say that it is about a sub-satellite point. This one is nothing but a sub-satellite point. And a point where we are supposed to be draw a tangent, because this is nothing but what? A point here. This one is nothing but a point T we can consider, and that particular point is nothing but the Earth station. Okay, that particular point is nothing but the Earth station. From this Earth station to the satellite, that is the line joining from the Earth station to the satellite. This is nothing but a satellite, we say. Okay, and then this is nothing but a tangent. Means what? We can say that a local horizontal here. This one is, we can say, it is nothing but a local horizontal. Okay, so this one we say a tangent here and a local horizontal, and a line joining from this local horizontal. Okay, line joining from this local horizontal to the to this point from this satellite Earth station to the satellite here. And this particular angle is called as a elevation. Okay, this particular angle is called as the elevation. So now this belongs to what? This belongs to your Earth now. This Earth is nothing but a circular. So this is about a sub-satellite point. There is no role right now. We just consider that a line joining from this Earth station to the satellite, and then this one is nothing but a local horizontal. Because we have this Earth, it is just like how if I redraw again, so Earth is nothing but a curvature here, and we have that antenna. So now this one is nothing but the local horizontal for this. In that case, this point from the Earth station to this particular local horizontal, that is nothing but the elevation angle. Okay, that is nothing but the elevation angle. Now, and sub-satellite point means what? From this satellite, this is the position of a satellite here, and line joining perpendicular to this Earth. And this is nothing but a sub-satellite point here. Right now, we are saying a sub-satellite point means line joining from this satellite perpendicular to the Earth station, or sorry, Earth. This is from the satellite point to the Earth, that is the body line is perpendicular, and that particular point is called as a sub-satellite point. And the angle the angle makes from this satellite to the Earth station, and this line, perpendicular line, and that angle is called as a tilt angle, or a, we can say that is about a nadir angle or a nadir point. Means in this case here, this angle is called as a tilt angle, or we can say a nadir angle, and that point is called as a nadir point. Okay, this vision from the satellite perpendicular. Okay, so in this case here, this one is about a nadir point or a nadir angle here. This one. Now in this particular case, okay, in this particular case, we consider that a angle. This one is nothing but a earth station here, and from this earth station we consider here. This is nothing but the coverage area of this particular satellite here. Now we have considered this one is a elevation. Now for this azimuth, okay, now that azimuth here, azimuth is nothing but what? The angle measured from the geographic north we consider. Okay, that is the angle measured from the geographic north at the Earth station to the trajectory of the satellite path. This is nothing but this one is nothing but a trajectory of the satellite path. Okay, or you can say a local horizontal on the local horizontal plane in the easterly direction. In the easterly direction. Now this one we say a geographical north here, and this is about local horizontal, and that angle is toward the easterly direction. Now we'll come back here. Now for that we need to redraw. Okay, we need to redraw the earth here to understand that what do you mean by the azimuth. Now this one is about your earth now, and for the given earth we consider this is nothing but the equator. Okay, this one is nothing but the equator. And a line joining from this what? A north to south point. This one is, we can say it is nothing but a north pole, and we can consider this is nothing but a south pole. This one is about what we can say a north and south pole. And supposed to be we consider a point. Okay, we consider that at Earth station or that particular point is located at this particular position now. This one is about a T. Okay, and we have a sub-satellite point is here. This one is nothing but a sub-satellite point. Okay, now this one is a sub-satellite. Now a line joining from here, we can say that at a trajectory here. This one is nothing but a trajectory. So that is nothing but what? A line. That is about a trajectory that is called as what we from Earth station to the sub-satellite point. And this one we can calculate that the angle, this nothing but angle from the north pole, okay, from this north pole toward the eastern direction, and that angle is called as a azimuth. Okay, that angle is called as a azimuth angle. Means this azimuth angle is measured from the geographical north pole. Okay, it is measured from the geographical north at the earth station. This was about at the earth station to the trajectory of a satellite on the local horizontal plane. Okay, this is about a local horizontal. T is nothing but local horizontal plane in the easterly direction. Okay, that is nothing but what we can say a elevate. That is called as a azimuth. Or in another way, we can say that azimuth of a satellite from a given particular point is the angle which the satellite direction makes with the direction of a true north. Okay, with the direction with true north here in the clockwise direction. Okay, this is in the clockwise direction. Okay, so these are nothing but a trajectory. Okay, that's nothing but a sub-satellite point. Or here we can consider that. Okay, this one is about, you can say, just like we also draw a sub-satellite point, or here we can say that is about a sub-satellite point here. So likewise, we can say that a projection of a satellite path on the local horizontal from this geographical north. So that's why the direction is here. Okay, from this direction is here. Okay, so that is nothing but the azimuth here. So generally we consider that a north pole. Okay, generally we consider that is a north pole, but we could not. There is a variation in what a magnetic north or a magnetic south. Okay, so that is about we consider the true north here. Okay, we need to consider that true north. We'll not consider that a magnetic north here. Okay, so whichever the north pole we consider, that is about a true north we have to be considered here. So we can calculate that what will be the azimuth angle and the elevation angle. So generally for the geostationary satellite, the maximum elevation angle can be of a 90 degree. Okay, this one, a maximum elevation angle can be of a 90 degree. So in that case, we consider that for a geostationary satellite, okay, for a geostationary satellite, for a geostationary satellite, the maximum elevation angle, okay, that maximum elevation angle that will be equal to the 90 degree. So geostationary satellite, it is to be considered always located on the equator. Okay, that geostationary satellite is to be considered always it is located on the equator there. And then that's why we can consider that this is nothing but the from this equator, and we consider that a satellite will be on this particular equator. So that's why so that angle will be a 90 degree here. If supposed to be Earth station, we have if it is situated at the higher latitude and that will be closer to the pole here. So we can say that is about a north pole. Okay, supposed to be consider that if for this earth station situated at a higher latitude and that will be closer to the pole, then in that case that elevation angle will be a small here. Okay, that case that elevation angle will be a small. So you just remember that if, or we can say that for a given earth station, okay, earth station situated at earth station situated at higher latitude, okay, is situated at a higher latitude, or you can say that a closer to the poles, closer to the poles. In that case, the elevation angle, that elevation angle is a very small. Okay, elevation angle becomes small there. Okay, so in that case, we can say that angle will be a small or it will become a small there. And in the case of the azimuth angle, okay, in the case of that azimuth angle, if you consider that a horizontal plane and from this particular north pole there, okay, so from this particular north case, if supposed to be satellite point will be here, so in that case it will be more than the 90 degree. So means we can say that the maximum azimuth angle, okay, the maximum azimuth angle is equal to what? That can be vary up to what? A 180 degree. Okay, maximum azimuth angle that will be varied from what? 180 degree. Because we have considered that azimuth angle is to be measured from the north, and that from the north toward the easterly direction. From the north toward the easterly direction. So that's why that will be the maximum will be of a 180 degree. If supposed to be consider that if that earth station is located on the northern hemisphere, in that case what happened, the azimuth angle of the satellite that will be visible and that can be greater than the 90 degree and less than the 270 degree. So in that case we consider that that earth station, if that earth station is situated in this particular northern hemisphere, so in that case that azimuth angle will be what? It will be greater than the 90 degree and less than the 70 degree. And if another case, if you consider that if the earth station is located in the southern hemisphere, okay, southern hemisphere, we can say that. So in that case, that azimuth angle can be greater than the 270 degree and less than the 90 degree. So we consider always that angle, look angles, that is to be expressed for the earth station in terms of what? A longitude and a latitude of the given earth station. So again we consider that we that is about a geometry of a satellite position, and we define that what are the look angles, and that will be defined in terms of the longitude and a latitude there. So we consider again, now this one is about the earth station, this is about your earth now, and from this earth it has some particular center here. Okay, so we consider that uh, that is a geocenter suppose, and this one is about a line joining from this to this. I supposed to be consider this one we have a north, and this one is not supposed to be a south now. And a longitude of the earth station, okay, so we can consider now this one is about a longitude of the earth station. So this one we can say that a given longitude of the earth station, okay, longitude of earth station here, and so we consider that is position of a satellite, okay, position of a satellite from the earth station now. So now in that case if we consider that here we have the earth station, here we have the earth station now, and the satellite position will be here now. This one is about a point here. We can say that is about a satellite position now. So in that case, if I draw a line from the Earth station to this satellite, okay, from this Earth station to the satellite, and then projection of a satellite from this particular point toward the Earth station. So in that case, that is nothing but a this one is a perpendicular from this satellite to this Earth station, and this particular point is called as a sub-satellite point. Okay, this particular point is called as a sub-satellite point, and this one is nothing but what we say a satellite altitude. This one is called as a satellite altitude, and this one line we called as a slant range. That slant range is nothing but the R here, and we supposed to be consider that from this particular Earth station, from this given Earth station to this particular sub-satellite point. Okay, that is about a line from this Earth station to this particular sub-satellite particular point here. So in that case, this is the what we can say a central angle of what from this Earth station to the sub-satellite point, and we can say that from this particular here we can say that is about your center of this particular Earth here. And we, at the same time there is a small variation. Okay, there is a small variation in what a longitude of the Earth station and this satellite there. Longitude of the Earth station and a satellite. Suppose I consider now the small variation in the longitude of Earth station here. In that case, that particular variation is called as a delta lambda. That is about a difference, and that about a point we consider. Okay, the delta lambda is nothing but what a difference between the longitude of the Earth station and the sub-satellite point. Difference between the longitude and a sub-satellite point. And this point M here, we say that that point is available on this equator now. So that's why we need to find out what will be the latitude of this Earth station from this particular line. So we say that here, this particular line joining from the center of this one, so it has a radius of r here, and from this to this line joining, and that is called as a elevation angle. Okay, that is nothing but we can say that the Earth station we can find out. Okay, that is nothing but what we say that a angle with respect to whatever the latitude we have, and then we consider that a latitude now from this given Earth station. This one is about a latitude here, and this m particular point we supposed to be considered that is on the equator. That point is on the equator. So this m point is there on the equator line now. It means we can have the equator plane, and this one is about a longitude. And another case, if you consider that this one is again belongs to the longitude of the Earth station or longitude of this given particular satellite there. And from this line joining from this is about the horizontal we say, we can say that this theta is nothing but the angle of a elevation there. This particular it is called as a it is a local horizontal or earth station horizontal. Okay, this line is called as local horizontal or a earth station horizontal, and that is called as a theta, and that theta is called as a elevation angle. Okay, this one is called as a elevation angle. And if you write the term here, suppose I am just this RE is nothing but what? A earth radius. This one is nothing but a earth radius now. And then this one we can consider that this theta E is nothing but what? A earth station latitude. And this delta lambda is nothing but what? A difference, because this one is about a difference in the terms of a longitude of the earth station and a satellite there. Difference in longitude of earth station and a satellite here. That is nothing but a difference there. And this particular E to S, that is about sample angle, that is nothing but a gamma. And this one is nothing but a central angle. That is called as a EOS. That EOS. Okay, that is nothing but we can say that is about a central angle. So generally we say that a satellite has a subsatellite point here, and that subsatellite point is generally on the equator. Okay, this one is nothing but we can say it is on the equator there, and the longitude of that particular subsatellite point, that will be lies in the plane of this particular paper here. And the earth station which has a latitude, okay, this one we can consider here. We have the latitude for this particular earth station of this, and that latitude, okay, and its longitude intersecting this particular on this particular equator at the point M here. Okay, this one is about we can say latitude, and this particular latitude that will be point here. And this particular central angle that will be formed by the line from the earth station and the satellite point. Okay, that is about a sub-satellite point or a satellite center point. So using that, you can calculate that what will be the that angle. We can say that is about a central angle there. So use the cosine law for the spherical triangle, that we can say that is about E, M, and S here. This one is about S point. E, M, and S. We consider that using the cosine law, using the cosine law for the spherical cosine law for the spherical triangle EMS. Okay, that's about EMS here. We can find out the cos of whatever the central angle we have, cos of whatever the phi E, we have the cos of delta lambda. Okay, we can consider that plus sine of phi, sine of delta lambda into cos of 90 degree, cos of 90 degree. And that will be is equal to what? That is about it. Phi into cos of a delta lambda. Okay, this one is about theta E or phi. Okay, so instead of that we have used a theta word here. So this one we consider it for phi. So that is about it. The latitude of the earth station now. And the delta lambda is the difference in the longitude and the subsatellite point. So using this particular equation, we can find out a slant range, what will be the R here? Then what will be the elevation there? What will be the azimuth? And what will be the tilt angle? What will be the tilt angle of this particular set? So we will consider again a diagram, another diagram here. We can consider that this one is about a center of the earth, and we supposed to be consider this one is about a point that is nothing but a north point. So from this, I supposed to redraw here that north and south pole, and we supposed to be consider that a point that is a sub-satellite point here, and this one is a point on of what you can say on the equator point of the satellite, sub-satellite point. Draw here, this one is the body point here. Draw here, this one is another point, and we say that this one is nothing but the equator now. Okay, this one is nothing but we can say that equator. Okay, so from this we say that this one is about your earth station, and line and joining from this earth station to sub-satellite point here, and that from earth station to this north. Okay, earth station to this giant, and earth station to this particular sub-satellite point, and that is nothing but a azimuth, as we have seen earlier here. Same thing we have seen. Okay, that azimuth means what? Line joining to this north, toward this particular north here. Or somewhere we have seen again. Okay, this one we consider that the earth station point and the sub-satellite point from this north pole here. Okay, that is nothing but the azimuth. Same here. This one is nothing but the azimuth here. And a difference in the latitude, sorry, longitude of the earth station and a satellite point. So this one is nothing but the difference in the longitude of the earth station and the satellite. That is nothing but a delta lambda. So this one we say here the earth station, this point E is called as we can say a earth station, and from this earth station toward the subsatellite, this particular point M on this equator here, we get this particular angle is called as a angle 180-degree minus that azimuth here. And this one is about a center. Okay, we can say that from this particular center, from this line, from this E here, and this one is the radius there, and this particular angle is called as a phi, and this one is about a center here. Okay, now consider again to understand that what do we mean by this slant range and all. So if I redraw this particular diagram again here with respect to the that center geocenter, we say this is nothing but O here, and from this particular point we'll have the location of a satellite that's about a P, and this one is the point we can say that this is nothing but a sub satellite point here. And we say that a earth station somewhere here I suppose to be considered this one is nothing but the earth station, and from this we can say that line joining here, and from this particular point toward the earth station now. This one is about a earth station. So this angle, if we make a perpendicular to this rad is nothing but a 90-degree now, and that becomes a theta here. That becomes a theta, and this angle is nothing but a tilt angle, and this range is nothing but from this point to this point is nothing but the R. That is about a slant range. Okay, that is nothing but a slant range. But to obtain this in terms of a right angle triangle, so we need to consider that projection here so that we'll get that actually this is become a 90 degree. Okay, this becomes a 90 degree this angle. So in that case, this particular point to this particular point we need to calculate, and this theta will be here now. And this one is nothing but what? We have this gamma. Okay, that is about a angle we have considered earlier. From this to this subsatellite point, this one is about the Earth radius, and from this subsatellite point to this satellite, that is nothing but a altitude now. And total is nothing but a R. Some books they have mentioned that R, or some books they have mentioned RS. Okay, like that's about the radius of the satellite from the center of the Earth to this particular point. Okay, so we can find out what will be this value of the R. So in that case, this one is the RE, and again this whatever the length we consider, this is again a RE here. So from this RE with respect to this particular theta, if we calculate, so that will be that length from this point to this point is nothing but a RE sin theta. Okay, this point is nothing but a RE sin point. So we can calculate that this particular length, okay, so in that case, this becomes a RE cos theta. So in the RE cos theta and RE sin theta. Now, so this particular length from this particular point is nothing but what? We have the this RE here, RE plus H. Okay, we have this RE plus H here in another way, and we have the another is about what? The RE cos theta, RE plus H and RE plus cos. So this angle it makes what? It is about a 90 degree here. In that case, this one is nothing but what? This particular distance is nothing but what? Under root of RE plus H, this one RE plus H, bracket square minus a RE cos theta. Okay, this one we will make here. So we can find out a slant range or a slant angle using that particular cosine angle, cos plane, or you can say that particular triangle here. So in that case, R square is equal to what? R square is equal to RE square plus RS square minus twice of RE RS cos of gamma. And that RS is about the that is about a satellite. Okay, whatever we can say that is length of the satellite from the center there. Or you can say that a radius of the geostationary satellite orbit here. Okay. And from this particular slant angle, if you further solve it, so we can calculate that R will be becomes what? That will be RS 1 plus RE by RS bracket square minus twice of RE by RS into cos of central angle. We can say that angle of elevation here. Okay, that angle of EOS. Okay, so we can say that that is nothing but a slant range. So in this given slant range, we supposed to be consider that Earth radius And then we can consider that a satellite radius here, that or length of from this center to the point satellite point, and this EOS here. And the azimuth we can calculate, we can obtain that azimuth, and that is the angle between the Earth station and the line joining the Earth station and the sub-satellite point. Okay, this one is about, you can say, the azimuth here. This one is about a satellite to this, whatever you can say, a north point, and this is the line joining from the Earth station to the sub-satellite point. And that angle is called as a azimuth here. So using this law of a sine for the spherical triangle, okay, using the law of sine for, we can consider that a spherical triangle. In that case, we can find out sine of az, that is the azimuth, sine of 90 degree is equal to sine of delta lambda divided by sine of this particular gamma here. And we calculate the sine of az here, that is azimuth, is equal to sine of delta lambda divided by 1 minus cos of cos square of phi e into cos of a delta lambda, and that will be 1 by 2. Or we say that directly, that azimuth is equal to sine inverse of sine of delta lambda to the 1 minus cos of phi is cos square phi, the cos square here delta lambda to 1. Okay, that is nothing but the azimuth angle. And the elevation angle, and that elevation angle is the angle, okay, that we can say that the theta here of the earth station, or that is the angle measured from what, from the local horizontal to the satellite point, local horizontal to the satellite point here. Okay, that is about the angle of elevation. Or you can say that this one is the satellite here point, and this is about the local horizontal. From this line joining, this is tangent here, so you can say that this particular angle is called as the angle of elevation. That is about a theta here. So that angle of elevation can be obtained using the spherical diagram or spherical angle diagram, and that will be obtained through the law of sine here. So Rs divided by sine of 90 plus theta is equal to R divided by sine of gamma here. Or we can calculate from this particular equation cos of theta is equal to Rs by R sine of alpha. Or we can say that Rs sine of this particular gamma here, we can say we have the radius of Earth, we have the radius from this particular satellite point, size of Re, Rs to cos of gamma here. And that is nothing but a, we can say that angle of this electron, or we can say that theta, and we can calculate that angle there. Or we can put that this particular value here, and we will get that whatever the tilt, that theta angle there. And another angle that is called as the tilt angle. That angle is measured at the satellite between the line joining from the satellite and the Earth station and the sub-satellite there. Line joining from the satellite there to the sub-satellite point. That angle is called as a tilt angle, or you can say that that angle is called as a nadir angle. This is about a that Earth station Here we have a satellite, and this one is about a sub-satellite point. So line joining from the satellite to the sub-satellite point, and line joining from this Earth station to the satellite point. That makes an angle that called as a tilt angle. So that angle can be obtained using the sign of a law, okay, used for this particular spherical triangle. So I'll write directly, okay, the angle. So before that, I'll write one equation there. That's about a sine of angle there. Okay, that law of a sine there is equal to Re by sine of a t here is equal to, we can say that Rs by sine of 90 plus theta is equal to Rs by cos of a theta. So if you solve it further, we'll get t is equal to sine inverse Re by Rs into cos of theta. So that is about, so now we can find out in terms of elevation angle, or you can say that angle of the tilt angle in terms of a cos of lambda. So sine of inverse here, Re by capital R into a sine of this gamma. Okay, so this way we can calculate that a tilt angle and all. So that is about this, all this term, and using this particular term, we will find out from what will be the elevations angle azimuth of a given satellite. So we will see the what will be the visibility of this particular satellite there, and we can calculate that what is the limits of visibility. So the limits of visibility means what? We have this particular satellite here, as we have seen earlier. As from this particular point, okay, nadir angle, we say position of this particular satellite from the Earth station with respect to whatever the elevation angle we have. So if that elevation angle is supposed to be